Assalamualaikum and hi everyone. My name is Khairunisa Shafia binti Kamarunizam with matrix number S70837. In this video, my group and I will like to present subject numerical methods. So, this is my group members.
In this chapter 2, I will present how we can estimate a normalized temperature parameter x for a thermistor circuit. Our sensor follows the nonlinear relationship e power of negative x equal to x, which we can rewrite as the function fx equal to e power of negative x minus x is equal to 0. We are given an initial interval of 0, 1, and our goal is to find the root to 4 decimal places until the approximate relative error falls below 0.05%. First, let's look at part A, the bisection method. This method works by repeatedly cutting our interval in half. In iteration 1, our midpoint is xr equal to 0 plus 1 over 2, which we got 0.5000. Evaluating the function give f 0.5 equal to 0.1065, which is positive. This means our root lies in the upper half, so we update our lower bound xl to 0.5. We repeat this process by iteration 2. Our new midpoint is 0.7500, giving a negative function value, which shifts our upper bound xu to 0.75. As we continue bisecting, our error gradually drops. It takes us 12 iterations to finally reach a point where our approximate error hits exactly 0.05%. At this point, our estimate temperature parameter is x is 0.5670. Next, in part B, we try to speed things up using the regular falsi or false position method. Instead of blindly cutting the interval in half, regular falsi connects fxl and fxu with a straight line and estimate the root where the line crosses the x-axis. We use formula x nu equal to xl minus fxl times xu minus xl over fxu minus fxl. In iteration 1, substituting our bounds give us an estimate root of 0.6127. By iteration 2, the error quickly drops to 7.08%. Because this method leverage the actual slope of the function, it converges much faster than bisection. By iteration 5, our approximate error drops to 0.02%, which successfully beats our 0.05% threshold. The final estimate root is 0.5671.
Assalamualaikum, my name is Abdul Rahman bin Halman, numerical S72111. Today I will present the solution for question 4.3, which involves solving a system of the linear equation using two methods. First method is Gaussian elimination with partial pivoting and the Gaussian-Seidel method. Question A, Gaussian elimination with partial pivoting. First, we are given the system of equation you can see in the slide. Using Gaussian elimination with partial pivoting, we first rearrange the row to place the larger pivot element at the top to improve numerical stability. After performing row operation and fourth elimination, the system is converted into the upper triangular matrix. Then, using back substitution, we option the final solution x1 equal to minus 1, x2 is 1, and x3 is 3. This shows stable and consistent solution. Okay, next question B. Gauss-Seidel method. Two iteration. Next, we solve the same system using the Gauss-Seidel iteration method. Starting with the initial guess 0, 0, 0. We then update each variable using the rearranged equation. After two iterations, the values become extremely large. x1 925,481.5, x2 minus 925,581.25, x3 300,263.61. These values clearly diverge instead of the converging. This indicated that the method is not stable for this system within the given iteration and initial guess. Okay, lastly, question C. Importance of the partial pivoting and the compression. Partial pivoting is very important because the coefficient 0.003 in the first equation is extremely small. Without pivoting, this can cause the large root of the error and the numerical instability. By the swapping row to place the larger coefficient as the pivot, we reduce the computation all error and improve accuracy. In comparison, Gaussian elimination with the partial pivoting give a stable and accurate solution -1, 1, and 3. Gauss-Seidel method failed to converge with the two iteration due to instability and the poor conditioning of the system.
My name is Tajawan and my number matrix is S72078. So today I want to talking about the chapter 5 and my question is 5.2 water tank system. So the height of water TH in the stronger tank is described by 18 equal to 0.03 dH over dt plus 0.09 hash. So giving the hash not equal to 0 using a step size of hash equal to 0.2 and 4 decimal place store out your calculation. So the A is determine the water level at T equal to 0.6 s using Euler method. So first we want to draw the table first and T equal to 0, 0.2, 0.4 and 0.6. So we want to find hash. So in this method we using formula is we want to find the dH over dt. So we can use the formula 18 equal to 0.03 dH over dt plus 0.09 hash. So we find and get the dH over dt is equal to 600 minus 3 hash. So first we want to find F0. So F bracket 00, so we get the answer is 600 and hash 1, the formula hash 1 is equal to hash node plus hash F node. So we get the hash 1 is equal to 120 and the second hash 2 is equal to 168 and also the hash 3 is equal to 187.2. So for the second question, we use midpoint method to find the hash. So we also draw the table T equal to 0, 0.2, 0.4 and 0.6. So in this method we use formula is K1 equal to F T node hash node and also K2 equal to F T node plus 1 over 2 hash and hash node plus 1 over 2 K1 hash and the hash equal to hash node plus K2 hash. So first we find the K1 and K1 the answer is equal to 600 and K2 the answer is equal to 420. So hash 1 is equal to hash node plus K2 hash. So we get the hash 1 is equal to 84 and also continue with this formula. So hash 2 we get the answer is 132.72 and the hash 3 is equal to 116.9776. So for B question, giving the exact solution hash t equal to 200 bracket 1 minus e power of negative 3t. So determine the relative true error percent for both method at t equal to 0.6s. So first, true error formula is equal to true value minus approximate value over true value plus times 100%. So for the Euler method, so the answer is get 12.14%. And the midpoint method, I get the answer is 3.57%. So for C question, based on the error author comment on the accuracy of the two methods. So first, we can see the midpoint method is more accurate than the Euler method because the midpoint method is similar relative true error is 3.57% and the Euler method is 1 12.14%. Therefore, the midpoint method giving a result calls for the essay solution t equal to 0.6.
My metric is S71815. So I will explain the calculation for question 6.3, which is to evaluate the definite integral of e power of 0.5x cos x from 0 to 2, and we will compare the two powerful numerical methods or approaches, which is the opposite trapezoidal and the rhomboid integration. First thing first, we map out our function by evaluating it at a key grid intervals from x equal to 0 to x equal to 2. This gives us our crucial data nodes starting at the 1.0000 and dropping down to negative 1.1311 at the upper boundary. First, we apply the multi-segment trapezoidal rule. We start broad with a single segment where n equal to 1. This row estimate yields a negative value of negative 0.1311. By doubling our segment to n equal to 2, our step size shrinks to 1, and the approximation jumps dramatically up to 0.9253. Finally, at n equal to 4, segment with a crisp step size of 0.5. Our trapezoidal estimation refines even further to 1.0509. While the trapezoidal rule gives us a great foundation, we can achieve vastly superior accuracy without calculating extra data points. We do this by constructing a rhomboid integration, a table using Richardson extrapolation. By combining our n equal to 1 and n equal to 2 columns, our first extrapolation gives us 1.1441. Combining n equal to 2 and n equal to 4 yields 1.1261. For the ultimate step, the second order extrapolation, we apply our formula with a denominator of 50 and converging beautifully on our final estimate of 1.1249. Looking at our error analysis, if we take our highly accurate rhomboid value as our true baseline, the standard trapezoidal rule at n equal to 4 leaves us with a noticeable relative true error of 6.5%. In contrast, the rhomboid method successfully hits a 0% relative error against this benchmark. This perfectly demonstrates how a rhomboid integration systematically eliminates leading mathematically error terms to give us high order precision with minimal effort. That's all from me. Thank you.